Hello IB, we're now looking at 12G, which is vectors in space, which means we're going into 3 dimensions. So up to now we've just looked at 2-dimensional vectors, but in 3-dimensional space we're going to be using the 3 axes, our x, y and z axis, or xyz axis. If you think of the YOZ plane, the YOZ plane, depending which pronunciation you want. So if we think about this plane, it's the plane involving the y-axis, O the origin, and z that axis. So if we think of that plane there being in the plane of the page, then the x-axis is coming out towards us. So that's just a way we talk about it. It doesn't mean it's always the case, because we can obviously take any perspective we like when we're in 3 dimensions. But that's often how you'll see it drawn. You'll see that the labels x are on the positive end of the line. So the label you put here means these are the positive values of x, these are the positive values of y, and these are the positive values of z. So z often makes sense because z's usually up is positive, down is negative. They've used dashed lines here to indicate the negative part of the axes. And so the coordinates of any point are going to have 3 values, x, y and z. So let's now look at a specific example where we've got our point P, we're going to call at 1, 2, 3. So you can actually set this up in GeoGebra. When you open up a GeoGebra package, then you can, let's go bigger, the options here, you can ask for view. We can go to 3D graphics. So that's what we've done here. We've gone to 3D graphics to set up these 3 dimensions. And here our x is our red axis. This is our y in the green, and our z going up is in our blue. So we've plotted the point 1, 2, 3, and that's this point A. All right? So that means it's 1 unit in the x direction, 2 units in the y, and 3 in the z. We can pivot this around and actually look and see, let's get off that pen, see what's happening. So this is our x-axis. So if we want to just look at the x-axis and we want to look down the z. So this is x, this is y. Here is our x value at 1 and our y value at 2. All right, so we can see that. If we want to see it from looking in at the x-axis, there we go. So we're now looking along from the x-axis. This is our y-axis. We can see y is 2 and z is 3. So depending what perspective you get, there's our little point hanging in space. You obviously won't have to draw any 3-dimensional things in your exams, but it's good to get a feel for it. They've, in the textbook, have used that rectangular prism to show your value in the x, the value in the y, and the value in the z. So our position vector, OP, is going to be either written in that vertical vector form, x, y, z, or in the component value, the unit vector form. We're using I, J, but because we now have another dimension, we're using K as our other unit vector. So we have X of these little unit vectors. So the one in the X direction will be the vector that is 1 in the X, nothing in the Y, nothing in the Z. The J will be just in the Y direction. So we've got 0, 1, 0. And the K will be just 1 unit in the Z direction. So it's 0, 0, 1. So here's another point, 5 minus 1, 0. If it's 0 in the Z, it means it's sitting on the XY plane. So there's our point B from the origin. Here's our point C from the origin, and this one we've written in unit vector form. 2i plus 3j minus 2k. That would be the same as 2, 3 minus 2. Just like this would have been equal to 5i minus j. And they're both vectors. So what if we want to get this point here, so this vector here that takes us from B to C, then we're going to do the same sort of mathematics or algebra we've done with the vectors earlier. So we just want to go 2, 3 minus 2. So we take the C, OC. All right, let's quickly write that in, reminding us of our notation. So we want, let me just write that up for you. Okay, just write it up. Remember, in your vector equation, you've got to have these matching. So BO plus OC, if they match, you can add those together. But we're not told BO, we're only told OB, so you do that switch, minus OB, and then we can rearrange them to do the C minus B. So here's our vector for C, 2, 3 minus 2, minus our vector for B, and now we can work that out, and we come up with, what have we got? Minus 3, 4, minus 2. So that's the vector for minus 3, 4, minus 2. Let's have a look at that on here. So you can set these up as well, just by inserting the coordinates of your point down here. So if I delete this one, then down here, where pointer? So we wanted brackets. What was the point again? 2, 3 minus 2. So we're going 2, 3 minus 2. So put those in, and that makes those 2 points. So here are 2 points. This point B, remember, was on the, we saw it was on that XY plane. It's got no Z value, so we can see it sitting on the plane there. And the C1 is sort of hanging in space. It's below the XY plane. It's got a negative Z value. All right, so let's spin that back around here. Okay, so we can now make the vector between those. You can do that with this option. If we want to create a vector, all right, what we do is select the starting point, then the end point. So here's our starting point. That's our end point. So we're going from B to C. So we come up with minus 3, 4, minus 2. That's what we got over here. So there's the vector. This vector is called U. We could rename that if we wanted to, but that gives us the vector between those 2 points. All right. Coming back here. Next thing we want to do, basically with the three-dimensional, we're just going to run through all the same calculations and things that we did with the two-dimensional. So if we want the magnitude of the vector, we want to see how long is this vector. Then we can see it's all tied in with a whole lot of right-angled triangles, which means if we know this length and that length, we can use Pythagoras because they're at right angles. But to get this length here, we need to first of all calculate this triangle, which is a squared plus b squared. So this hypotenuse here is a squared plus b squared. Add that to c squared and we get the overall length. So OP squared is a squared plus b squared plus c squared. OP is the square root of all those. So that is similar to what we saw with our two-dimensional vector, but here we now have v1 squared plus v2 squared plus v3 squared. So using the example we just did here, where we had BC is minus 3, 4, minus 2. So substituting those values into our formula, minus 3 squared plus 4 squared plus minus 2 squared gives us root 29. We can actually find that out over here. If we want to get the distance or length, we want to get the distance between 2 points. So select the 2 points, the segment or the polygon. So we want to get this distance to here, and we see that it comes out as 5.39. And if we actually took the square root of root 29, we'd come out with 5.39. So we can do that on both GeoGebra and algebraically. Next, the vector between 2 points, just as we did AB, is AO plus OB, which is equal to, often, if we're not told AO, so therefore we want OB minus OA, so the final point minus the initial point, do that normal subtraction. If we want the distance between those points, we just substitute it in those values, but they come from subtracting the x values, subtracting the y, subtracting the z, and squaring them. So 2 different rules, and we can see the same as the distance between 2 points that you would have done in years 9 and 10. If I want the midpoint of 2 points, we just take the average of the x values, average of the y, average of the z, just the same as we did in 2-dimensional. If 2 vectors are equal, then the direction, these will be the same. So A1 will equal B1, A2 will equal B2, A3 equals B3. So it doesn't mean that they're in the same location, it just means they're the same magnitude and same direction. They could be opposite directions, but they're going to be parallel, but they won't be equal. All right, so just be careful. If they're equal, it's got to be the same of everything. If you get 2 parallel vectors, then they make a parallelogram. So that, realizing that no matter what vectors we have, if I have this vector and the same vector here, then I can make them into a parallelogram anywhere. And it may not be in the same, like it might not be in the XY plane, it could be at any angle in 3 dimensions. This one here, there's a range of geometric proofs that you can do. So here we've got 3 points. These are the coordinate points. So remember, the coordinate points are not the same as the vector points. So this is 0, 4, 4. Draw any random triangle. You don't have to know exactly where these are. Just plot them up and record your values, your coordinate points. If you want to show these as a vertex isosceles triangle, you've got to show that either PQ equals PR and doesn't equal that, or these 2 are equal and not equal to this one. So you basically have to work out the 3 lengths. So if you're wanting the lengths, you obviously need to say, first of all, start with P, let's do PR, get that vector. So the vector for PR will be 1 minus 0, 4 minus 4, 3 minus 4 equals 1, 0, minus 1. So now we can get the length of PR. You could have done that all in one step if you wanted to. That's meant to be a nice straight line. So we're going to get the square root of 1 squared plus 0 squared plus minus 1 squared equals 1, 2, root 2. So now work out the others and see if they're equal to or not to root 2. We'll come back to that one in class. This one here, if we want to find the distance of a point from the origin and to the x-axis. So think about where that point is. If we come out, say, 4 out this way, minus 2, so if we come out, let's say it's about 4, minus 2 out in the y, and up 3, it's just a rough one, So that's 3, this is -2, and that's 4. How far is it from the origin? You're trying to find that length. How far from the x-axis? I'll leave you to think about that one. How far is it from the XOY plane? I'll let you think on that one, and we'll talk about those in class. The last one here is, if we know that we have this like equation with vectors, that a minus 4 is equal to that, then it makes sense that we can say that this, if that vector is the same as the other one, then they must be equal. So we can go a minus 4 is equal to 1, which means a must equal 5. So you can go through and solve for A, B, C. This one, given this is a unit vector, find the value of k, same as you did for two-dimensional. So I'll leave you to have a go at those, and we'll do them in class, and then we'll talk through this example in class as well. That's all written up here, and yeah, we'll just talk about that one in class. So thanks for listening, and yeah, come with any other questions you may have in the lesson time.